Chapter 16 in the abstract algebra series is on cyclic groups, and problem number 1 says to find all the subgroups of C16. The order of C16 is 16. In any subgroup, the order of any subgroup, rather, would have to divide 16. 1 divides 16, so we know we have the identity element. And we know that 16 divides 16. And that's the entire group itself, because every group is a subgroup of itself. And of course, 2 divides 16, which gives us the subgroup containing the elements e and r to the power of 8. And the next one is the one I want to focus on just to illustrate. We know that 4 divides 16, which means we would have a subgroup of order 4. If we look at the subgroup of order 4, starting at the identity, if we move over r to the power of 4, that would take us to this position. And if we just keep generating from that, r to the power of 4 times r to the power of 4, that moves us to r to the power of 8. And then if we continue to apply r to the power of 4 in a likewise manner, then that would give us r to the power of 12, and finally r to the power of 16, which is r to the power of 0, and of course that takes us back to the identity. So r to the power of 4, operating on itself 4 times, will take us back 1 complete circuit. And likewise, if we were to use r to the power of 2, if we were to use r to the power of 2 and continue to allow it to generate itself, then we would go from r to the power of 2 to the power of 4 to the power of 6 to the power of 8 to the power of 10 to the power of 12 to the power of 14, and finally back to the identity. So these are all the subgroups of C16. Number 2, find the subgroups of Z17. Well, 17 being prime only has 2 divisors, 1 and 17. Well, that just leaves us with 2 subgroups. That's going to be the identity subgroup, because it has an order of 1, and 1 divides 17, and of course the group itself, because 17 divides 17. Number 3, what is the order of r to the power of 4 in C16? Well, if we want to look at r to the power of 4 in C16, we could go back to the picture, and we know that r to the power of 4 has an order of 4. So if we start with the identity and we allow r to the power of 4 to generate, it's going to move into this position first, and applying r to the power of 4 again is just going to turn the hand of the clock to this position, r to the power of 8. And then if we apply r to the power of 4 again, we get r to the power of 12. And we can see that the order is 4. It takes 4 applications of r to the power of 4 to complete this cycle. There's also a formula that we can use, and that formula simply says if you want to know the order of a generating element, you take the order of the set, which is n, and you divide that by the greatest common divisor of n and k, where k is the power of the generating element. So 16 divided by the GCD of 4 and 16 gives me 16 over 4. And there we go, using a little algebra there, we can see that the order of r to the power of 4 is 4. So we get the same answer. Number 4, what is the order of r to the power of 6 in C16? Again, if we apply the formula using 16 for n, and we're going to divide by the GCD of the 16 and 6, because 6 is the order of the generating element, and we get 8. If we want to list those, starting with r to the power of 6, we would have r to the power of 12 as a follow-up. And of course, r to the power of 18 is going to be r to the power of 2 because we're in C16. And that gives us r to the power of 8 next, r to the power of 14, then 4, 10, and finally takes us back to the identity, and we completed a cycle because if we apply r to the power of 6 after the identity, it takes us right back to where we started from. Number 5, what is the order of 6 in Z16? Well, Z16 is isomorphic to C16, being finite groups, and they are cyclic, as we can see. If we want to apply the 6 each time, that's going to give us 6 followed by 12. And if we apply 6 again, of course, being in Z, we're using addition as our property here. So we have 6, 12, 18. And of course, 18 in Z16 is 2. Let me erase that. And let's apply the 6 to the 2. That gives us 8. And if we apply 6 to 8, that's going to give us 14. And if we apply 6 to 14, that's going to give us 20, which is equal to 4 in Z16. And let's add 6 more. That's going to give us 10. And add 6 more. That's going to give us 16, which is 0 in Z16. And of course, if we add 6 again, that would take us back to our starting element, which means we've completed a cycle. And as you can see, rather sloppily there, that we do have 8 elements. Problem number 6. Find all of the generators of Z20. All integers in Z20 that are relatively prime to 20 are generators. And we have the list 1, 3, 7, 9, 11, 13, 17, and 20. Why do they have to be relatively prime in order to generate Z20 in its entirety? Well, if you take an integer that is a divisor of 20, let's say 4. Well, 4 goes into 20 5 times. So you would only generate a set of 5 elements. That's not going to give you all of the integers in Z20. Likewise, if you were to use 10 as a potential generator, it would only generate 2 elements. That would be 10 and 0. So in order to generate the entire set of elements, you have to choose an integer that is relatively prime to n. Number 7, list all the elements in the subgroup generated by r to the power of 6. And this time we're working in C15. If we start with r to the power of 6, and if we keep applying it throughout the cycle, we can see that we go from r to the power of 6, then to the power of 12, back to the power of 3, because 12 and 6 is 18, but 18 is equal to 3 in C16. And if we add another r to the power of 6, that gives us r to the power of 9. And then finally, r to the power of 15, which is the identity. So we can see that all of the elements generated by R6 gives us 1, 2, 3, 4, these 5 here. Number 8, under what circumstances is the order of G equal to the order of G squared? Well, remember that according to our formula, the order of G is n, and the order of G squared is going to have to be, let me get my pen here. The order of G squared also has to obey the formula, so it is going to be n And we're just going to substitute the order of g for n. So the order of g squared is still n divided by the GCD of n. And of course, the power of the potential generator, which is 2. So we applied the formula here. We just used a substitution. We substituted the order of g in place of n. And then we have to go through and look at a couple of possibilities. Number one, if the order of g happens to be odd, because we know the order has to be either odd or even. If the order of g is odd, then we know that our denominator is 1, because 2 is even, and 2 has the only divisor of 2 in any odd number is going to be 1. So if the order of g is odd, then our denominator has to be 1, leaving the order of g equal to the order of g squared. What if the order of g happens to be even? Well, if that's the case, then the order of g squared is going to be 1/2 the order of g. And the only way that could possibly be equal would be if g is infinite. And that takes us into number theory. So I'll just leave it at that. Number 9. Number 9 says to list all the elements in the subgroup generated by 6 of Z10. And the element starting with 6 would be 6, 2, 8, 4, and 0. And again, we get that by starting with 6, since that's the generator, and we just continue to add 6. 6 plus 6 is 2, 2 plus 6 is 8, 8 plus 6 is 4, and then finally, if you add 6 to 4, you get 10, which is equal to 0 in Z10. Number 10, list all the elements in the subgroup generated by A of S sub 6, where A is equal to, let me add some notation here. A is going to equal this permutation, and we're looking for all of the elements in the subgroup generated by this permutation. So all I did was I continued to apply this permutation on itself n times. For example, in order to figure out a to the power of 2, then I had to multiply this permutation by itself. And again, if we're doing permutations, then we're going to be doing it in a composite fashion. So we will have to start our operation from the right side and work our way to the left side. For example, if you want to figure out what a to the power of 2 is, we would end up having to multiply a times itself. And let's see if I can do somewhat better with this drawing today. So let's see, we have 2, 1, 6, 4, 3, 5. In order to find a to the power of 2, again, we would start on the left side, and we can see that 1 matched to 2, and then 2 matched to 1, which means 1 matched to 1, and then 2 matched to 1, and 1 matched to 2, so 2 matched to 2, 3 matched to 6, and 6 goes to 5, which means 3 goes to 5, and so on. 4 would go to 4, 5 would go to 6, and 6 would go to 3. So this would be a to the power of 2. So how do we figure out a to the power of 3? To figure out a to the power of 3, I just took a to the power of 2, which we just figured out, and I would multiply it by the given permutation a, and we would derive a to the power of 3, and just continuing on, multiplying a to the power of 3 times a, and then we get a to the power of 4. Working our way around, we get a to the power of 6. And sure enough, if you apply a to the power of 6, it takes you back to the beginning, which means you've completed the entire cycle. Note that for each a to the power of n, we could have expressed the permutation in standard cycle form. In other words, a squared could have been written using cycle notation 1, 2, circle 3, 6, 5. We could have said a to the power of 6 is equal to just the cycle containing 1, which is the identity.